Hi everybody, in this video I will talk about four variables P, V, N, and T and how they relate to gases. P is pressure in ATMs, V is volume in liters, N is the number of moles of gas in moles, and T is the temperature in Kelvin. So always make sure that when you have a pressure, a volume, an amount of gas in moles, and a temperature, make sure that they are in these units here, or else the numbers will come out weird. And the equation that relates these four units is called the ideal gas law. It's written as PV equals nRT. And this time, the R is not 8.31. This time, R is 0.0821. We only use 8.31 when we are looking at things related to energy in the unit joules. And since this formula has ATMs, liters, moles, and Kelvin, none of these units have anything to do with joules, and as a result, the R will not be 8.31, but it will be 0.0821. In the future, you will see when R is 8.31, and this happens because we are looking at energy. So in electrochemistry, we are looking at electrical energy, and as a result, we use 8.31, but for now, we're going to use 0.0821. So let's talk about why this is called the ideal gas law. It is called the ideal gas law because we are assuming a few things in order for it to be ideal. The ideal gas law assumes that 1. Gases are made up of a lot of particles in random motion. 2. The volume of gas particles is negligible in comparison to the volume occupied by the gas. And this goes back to the point of how the volume of these gas particles are super small in comparison to the volume of the container. And that's why the volume of the particles are negligible. And 3. No force of traction or repulsion acts on molecules. However, molecules can still experience elastic collisions with other molecules and with the container. So this looks very similar to the kinetic molecular theory, and that's because it probably is. So now that we have the assumptions out of the way, let's try using the ideal gas law in a problem. Let's just say that we have a balloon that's filled with helium, and the pressure exerted by the helium is 1.30 ATMs, and it fills a volume of 0.331 liters, and the temperature in the balloon is 30.0 degrees Celsius. How many grams of helium would be in the balloon? Well, this problem can be done using PV equals nRT. So our P will be 1.30 ATMs, and I'm not going to write the units because I know that ATMs is the unit I want, and V is 0.331 liters, and this is equal to the number of moles of helium times R, which is 0.0821, and that is multiplied by the T. And remember, T is in Kelvin, but we have degrees Celsius, so we have to turn degrees Celsius into Kelvin. So this can be accomplished by doing 30.0 degrees Celsius plus 273.15, and we get 303.2 K. So let's write that, 303.2 K. And once we multiply this all out, let me erase the K and just write 303.2 because we don't really need the units if we know what we're multiplying. And we calculate N to be 0.0173 moles of helium inside the balloon. So how do we find the grams of helium inside the balloon? Well, that's just converting moles to grams using molar mass. So 0.0173 moles of helium times the molar mass of helium, which is actually 4.003 grams per mole, and we get an answer of 0.0692 grams of helium. And note that I am using significant figures because in science, always use significant figures in your work if possible. So when we talk about moles of gases indicated by the letter N, the moles of gases, you could have moles of helium, moles of neon, moles of nitrogen gas, moles of oxygen gas, even moles of methane gas, even moles of nitrogen dioxide gas, and the list goes on and on. So when you're finding the moles of oxygen gas, you are not finding the moles of O, you are finding the moles of O2 because oxygen gas is naturally found as a diatomic molecule. So when they want you to calculate the mass of oxygen gas, you have to know that the moles that you're calculating is O2 because oxygen gas is O2 and not O. So now that the misconceptions are cleared, let's talk about the relationship between the variables in the ideal gas law. So let's just say that we had a gas in a container, and let's just say there was a movable piston that moved up and down, and let's just say this container had a certain number of moles of gas, and it was at a certain temperature. So let me just draw the dots as the particles of gas. And let's just say that this container had the gas, and the gas, which we will label in stage 1, has a pressure of P1 and a volume of V1. So let's just say that the person moved the movable piston down, and now the gases are more clumped up, but the amount of gas and the temperature of the gas is still constant. Now, this will be the second stage, and by moving the piston down, we will have a new pressure P2 and a new volume V2. So let's use PV equals nRT to derive a relationship between these four numbers. So P1 V1 equals nRT because N and T are constant, so I'll use those as the variables. And on the right-hand side, it would be P2V2 equals nRT. So notice how this is equal to nRT, and notice how this is equal to this. So thus, I can plug this into here, since these two are the same, and this is a process called substitution. So in the end, we have P1V1 is equal to P2V2, and this is called Boyles Law. Boyles Law tells us that if we start off with a certain pressure and a certain volume, P1 and V1, and maybe we move the piston down and we change the volume to V2, then it follows necessarily that we can calculate P2, because if we have 3 of the 4 variables, then we can calculate the 4th variable. So for example, if I gave you these 2 pressures, and I changed the volume of the container and kept N and T constant, then there will be a certain pressure that's associated with that. Now, I'll show you how to do that later using examples, but for now, let me derive one more thing. So we know that P2, V2 is equal to nRT, and we know that N, R, and T are constant in the process, while P and V can change because it changed from P1 to P2 and V1 to V2. So those 2 are variables, but these 2 are constants. We can change this into K. So we know that P2, V2 is equal to K, so therefore we can substitute it in, and we could say P1, V1 is equal to K. And since P and V are constantly changing, we don't have to label it as P1, V1 anymore. We could just say PV equals K. And this leads us to something very special. The form PV equals K is similar to the form XY equals K. And if you remember from your math class, if you multiply X and Y together to get a constant K, it forms a graph that looks like this, where the curve is asymptotic to the x-axis and the y-axis, which means that it won't touch it, but it'll get super close to it. So in the same way, this relationship PV equals K shows a curve like this, and P would be here and V would be here. And this is called inversely proportional. So P and V are inversely proportional, and it comes in the form where you multiply two variables to get a constant. So now that we went through the long way to derive these, let me show you a shortcut to derive Boyles Law without having to do all these substitutions. So simply just write out the ideal gas law, PV equals nRT, and we know that Boyle's law compares pressure and volume, assuming a constant moles and constant temperature. So what you do is that you ignore everything that's not these two. So I'm going to ignore all that, and we get a relationship saying that PV is equal to K. And to get Boyle's law, simply just say P1V1 is equal to P2V2, just by kind of doubling it over. And that's how you derive the laws in a faster process. But of course, the legitimate process is by doing the thing that I did before. So now let's derive a relationship between temperature and volume. So let's do it legitimately. Let's draw the two pictures. And we want to change the temperature and volume. So this will have a T1 and a certain volume, and this will have T2 and a certain volume, and we will keep pressure and the amount of substance or moles constant in both containers. So this will have, a piston there, and this will have a larger volume, V2. So let's find a relationship between T and V based on the ideal gas law. So we will write PV1 equals nRT1, and let's write PV2 equals nRT2. And now let's try to find a relationship between V2, T2, and V1 and T1. So what I would do is I would move the constants to the left and the variables to the right. The variables are the things that are changing. So for example, T1 is becoming T2, and since that's changing, it is a variable. So in order to do this, I'll just divide everything by P, and by, I would divide by PT1, and you'll see what happens. So on the left hand side, the pressures cancel out, and you get V1 over T1 is equal to NR over P, because the T1s cancel out on the right side. So I get this formula, and I'll do that for the right hand side as well. So we'll get V2 over T2 is equal to NR over P. So we can substitute V2 over T2 for NR over P. So this could go over here, and we end up with V1 over T1 is equal to V2 over T2, and this can be rewritten as T1 over V1 is equal to T2 over V2, whichever way you want to write it, but they're both Charles's law because they relate T1 V1 and T2 V2. And how can we tell what relationship this is? Well, let's just substitute V2 over T2 for not NR over P, but instead K. So if this is K, then we can say V2 over T2 is equal to K, and we can say that V1 over T1 is equal to K. And since we don't really need the ones anymore, then we could just say V over T is equal to K in order to show that the V and T are different and they can be constantly changing. So if we graph this, what would it look like? Well, we can move things around. We can claim that V is equal to KT, and this looks like Y equals mx. And remember, m is a constant, so it's just like K, and x and y are changing, just like t and v are changing. And if you know from your math class, y equals mx is the equation for a line that goes straight through the origin. So our x would be t and our y would be v. And this is the relationship between t and v when graphed for a constant pressure and amount of substance, or moles. So this is called directly proportional, and I'll actually erase the ink and write directly proportional here. So proportional. And for Boyle's law, it's actually inversely proportional. And in order to derive Charles's law without going through all that math, we can just write PV equals nRT, and we want to compare the two variables, and in Charles's law, we are comparing T and V, so we will, I guess, try to make it so that T and V are on one side, so we would divide both sides by T, and we would get PV over T is equal to NR, and then we want only V and T, so we would divide both sides by P, and we would get V over T equals NR over P. And as a result, we just derived the relationship between V and T, because we can simply cancel this out, turn it into K, so V over T is equal to K, and we can rewrite this by doubling it up, so V1 over T1 is equal to V2 over T2, and this is known as Charles's law. Now, the last law I am going to derive is Avogadro's law. Avogadro's law compares moles and volume. So PV equals nRT. We want the volume and moles to be on one side, so I would just divide both sides by moles, and I would get PV over N is equal to RT, and I would divide both sides by P in order to get V and N alone, so I would get V over N is equal to RT over P. And we can change this into K, so V over N is equal to K, or V1 over N1 is equal to V2 over N2. And this is Avogadro's law. And since this looks just like this, and we said that Charles's law is directly proportional, then Avogadro's law is also directly proportional. And if you draw the graph, you would see that the volume is directly proportional to the number of moles, which is indicated by a line. And if you wanted to prove this, I would just use this. So V over N is equal to K, and multiply both sides by N, we get V equals Kn, and this looks just like Y equals mx, and that's the equation for a line that goes through the origin. So we found the relationship between volume and moles by using the ideal gas law. And do these laws make sense in the real world? Well, I think they do. For Boyle's law, we can imagine, I guess, two containers. The first container containing a piston and some particles, and we know that the number of moles of particles and the temperature is constant, so N and T are constant. And if we decide to decrease the volume by using a movable piston, the volume will decrease, but since the particles are more clumped up now, the pressure actually increases. So they are inversely related, and it makes sense. Now let's see if Charles's law makes sense. It relates volume and temperature for a certain pressure and moles. So let's take a hot air balloon. A hot air balloon, when deflated, let's just say that the balloon is deflated and it has a certain number of moles and a certain pressure that will stay constant. So in the hot air balloon, if you, I guess, heat it up using a fire, then the hot air balloon will expand. And this goes to show that when temperature increases, the volume will increase consequently for a constant pressure and moles of gas. So we are assuming that pressure and moles of gas are constant, but they're not actually constant. But for simplicity, if we assume they're constant, then this makes sense, since in a hot air balloon, if we heat up the gas will expand, and thus the volume will increase. So Charles's law makes sense. Now, does Avogadros Law make sense? Well, let's think about this. Let's just say that we have a balloon with not a lot of gas in it, and let's just say that we added more gas, so the moles will increase. Now, for a certain pressure and temperature, which will stay constant, so P and T will stay constant. Now, for a certain pressure and temperature, if we increase the amount of gas, then the volume will naturally increase. So you can think of it as just putting more gas in, and if there's more gas, then there's more volume. And therefore, Avogadro's law also makes sense in the real world. Now, there's one more law. It's called the combined gas law. The combined gas law compares pressure, volume, and temperature. Now, how do we derive this? Well, you could take PV equals nRT and make it so that PV and T are on one side. So PV over T is equal to nR. And since we're assuming N and R are constants, then this can be rewritten as K, and thus PV over T is equal to K, or P1V1 over T1 is equal to P2V2 over T2. So this is the combined gas law. And there's one last equation that I find the most useful. It is when you consider all the variables. In other words, you consider P, V, N, and T as variables, with the only constant being R, and R will be constant no matter what, since by definition R is a constant. So this would be PV equals nRT, and divide both sides by NT, and we get PV over NT is R, and R is a constant, so PV over NT equals K, and we can rewrite this as P1V1 over N1T1 is equal to P2V2 over N2 times T2. And I know that's kind of clumped, but as you can see, this is my favorite equation to use because it encompasses all of the variables at once. And I'll show you why this form is my favorite form, even though it's not one of the official forms like the 4 I just showed you. But I'll show you that it's really useful. So let's look at this question. Let's just say we have a balloon, and at 2.31 atms and 25 degrees Celsius, the balloon has a volume of 0.201 liters. But when the balloon is dipped in liquid nitrogen, it turns the temperature into negative 100 degrees Celsius, and the new volume is 0.170 liters. Now the question is, what is the new pressure? Now, since a balloon is enclosed, we can assume that the moles stay constant, and thus our three changing variables are P, V, and T. Now we could definitely use the combined gas law, but I'll show you why this is my favorite. So P1V1 over N1T1 is equal to P2V2 over N2 times T2. Now, if we know that N is constant, then we could just cancel it out from both sides since they're the same. And this is just doing some algebra, and by doing that, we get the combined gas law. So notice how this equation right here is able to simplify into this by assuming that N1 and N2 are identical. So that's why I like using that equation, because you can turn that into anything else, such as the combined gas law. So if we plug the numbers in, P1 is 2.31, V1 is 0.201, and T1 is not 25, but 25 plus 273.15, since we want all our units to be in the 4 units that I mentioned at the beginning of the video, and this would be set equal to P2, which is just P2 because we don't know what that is, and V2 is 0.170, and it seems like T2 is negative 100 plus 273.15, and once you solve this equation, you get that P2 is equal to 1.59 atms. So let's do another question relating to the ideal gas law. So the density of a gas is found to be 0.118 grams per liter, and the volume of the container is 2.00 liters. The temperature is 25 degrees Celsius, and the pressure in the container is 0.143 atms. So my question is, what is the molar mass of the gas? So at first you might think, wow, this is a pretty hard problem, but we can break this down. So let's find the units for molar mass. Molar mass is grams per mole. So moles is the N in PV equals nRT. So I see a relationship there, and I see grams here, and I know that I can convert grams to moles using molar mass. So that's another hint. So let's see how we could apply PV equals nRT. We know what P is, so we know that P is 0.143, and we know that the volume is 2.00 liters. And what's our N? Well, we don't know what our N is. What's our R? Well, 0.0821. And our T is just 25 degrees Celsius plus 273. Now let me not write the units to avoid confusion. And doing the math, we get N, or the moles of gas, is equal to 0.0117 moles. Now, how can we use the moles of gas to find the molar mass? Well, we know from experience that the moles of gas times the molar mass is equal to the mass, because this is moles and this is grams per mole, and the moles cancel out to leave grams. So we can use this to find the molar mass, and we know that N is equal to 0.0117. So what is the mass of the gas in the container? Well, don't you think that if we multiply the density times the volume, we will get the mass? Well, yeah, let's try that. 0.118 grams per liter times 2.00 liters, and we will get 0.236 grams of gas. Now that we know that, we can put up an equation. So 0.0117 moles times the molar mass is equal to 0.236 grams. And solving this, you get that the molar mass is equal to 20.17 grams per mole. And this most closely resembles the molar mass for neon. So the gas inside this container is neon, and we figured that out by using a periodic table and its molar mass. Now, here is a shortcut equation written in blue that relates density to molar mass. So molar mass is mm, and density is this P-looking symbol, and it's called rho. So feel free to pause the video if you want to see how I derived this formula from PV equals nRT. Now let me tell you a little secret in chemistry that will carry you very far in science and even in math. Unless you are very good at memorizing, it's better to do things from scratch and think about it just like I did, such as in this problem, rather than just plugging and chugging into this formula to get your answer. Because in science and in math, doing things from scratch without a pre-made formula helps develop your critical thinking skills, and that's very important in chemistry and in other courses that you will take in the future. The only time I memorize formulas is when I find it easier to do the question with the formula, or if it's impossible to derive. For example, PV equals nRT. I don't really know how to derive that. I just simply memorize it, and it's really catchy too. So I memorize that because it's easier for me personally. And meanwhile, I don't memorize this because I can easily solve this problem by thinking about it logically instead of plugging and chugging. So it saves a lot of brain space, and that's an important lesson that I just wanted to share. So over here, I solved the previous problem using the pre-made formula. And note that the answer is 0.02 off, but that's because of rounding errors from the first time. and that's perfectly fine. It still works. And note that the density must be in grams per liter in order for this to work. And have a nice day.